Welcome to the CVPR 2022 tutorial of OpenMMLab. OpenMMLab, a foundational platform for computer vision research and production. I'm Wei Zhang from NTU MMLab. So OpenMMLab is an open source algorithm platform for computer vision. It aims to provide a solid benchmark and promote reproducibility in academic research. It has released more than 20 high-quality codebases in various research areas. Till now, OpenMMLab has implemented more than 300 algorithms and released more than 2,000 checkpoints. So today's schedule contains 5 parts. First, Dr. Kai Chen will give us an overview of OpenMMLab and its recent updates. Then Professor Chen Zhiroi will discuss about improving video super resolution with enhanced propagation and alignment. In the third part, Dr. Han Hu will bring his recent thoughts about convergence of architecture and learning methods in computer vision and other AI fields. After a short break, Professor Han Zhao will introduce vision-centric 3D perception for scalable autonomous driving. Finally, Hao Dong will discuss about action understanding in a human-centric view. So, okay, let's invite Dr. Kai Chen to bring us an overview of OpenMMLab and its recent updates. I will firstly briefly introduce Kai. Dr. Kai Chen is currently a young scientist in Shanghai AI Laboratory, leading the Department of Open Source Algorithms, OpenMMLab. He received his PhD in 2019 from the Chinese University of Hong Kong and a bachelor's degree from Tsinghua University. He has published more than 20 papers on top conferences and journals in computer vision and won several awards on international challenges. OpenMMLab has gained more than 50,000 stars and involved nearly 1,200 contributors on GitHub. It is a highly influential open source algorithm system for computer vision in the era of deep learning and has had a wide influence in academic and industry. So, are you ready? Yeah.
Okay. I need to share the screen. Oh, okay. Thanks, Wei. Hello, everyone. I'm excited to present OpenMMLab, the open source platform for computer vision. Today, I will give an introduction to OpenMMLab and share some recent progresses. My talk today consists of 4 parts. Firstly, I will give an overview of OpenMMLab, and then I will share some recent updates of OpenMMLab. Next, I will talk about the technical design, and finally, I will give a quick tour for developers and researchers. OpenMMLab shares one common architecture, and the unified architecture supports all the code bases. Based on the unified architecture, OpenMMLab supports more than 30 research areas. It covers various areas of computer vision like classification, detection, segmentation, etc. And it now supports more than 300 algorithms. It implements both classical and the most recent algorithms. And also it released more than 2,000 pre-trained models. It provides unified areas currently. These are research areas currently supported by OpenMMLab, including both high-level and low-level tasks. We can see that most mainstream topics are covered, including learning methods such as self-supervised learning, feature learning, and also weakly supervised learning. And also it covers detection, segmentation, and for video understanding, multi-object tracking, etc. Now I will give a brief view of the history of OpenMMLab. It was first released in 2019, and initially there are only 2 packages, MMCV and MMDetection. In 2019, 4 new code bases were developed, and in CVPR'22, we support more mainstream tasks such as classification, segmentation, 3D detection, etc. In the last year, we keep open sourcing toolboxes for various areas and also collaborate with colleges and research institutes to work on more directions. In the future, we will extend the boundary of OpenMMLab and more is coming. OpenMMLab is based on PyTorch, the most popular deep learning framework. We developed a foundational library for computer vision, MCV, which implements common modules like image processing, video processing, and modules, and also CUDA operators. And also it provides a unified training engine, which supports all the code bases. Based on MCV, we have code bases for different research areas. For image understanding, video understanding, and also image editing. Yeah. These code bases focus on the model training and cannot be applied to industrial applications directly. Thus, we developed MDeploy for model deployment. It bridges the gap from research to production. OpenMMLab has gained great community impact as its rapid development. It has received about 60,000 stars on GitHub, surpassing PyTorch. It is noted that OpenMMLab is not a competing library of PyTorch, and this is not a fair comparison. We just stress the impact of OpenMMLab by comparing it to PyTorch. OpenMMLab users now are from more than 110 countries and regions. And also it covers more than 600 colleges and research institutes. Every year, the release checkpoints are downloaded more than 1 million times. We have also built a community for developers. There are more than 1,000 contributors who have committed codes to OpenMMLab projects. On GitHub, there are more than 500,000 lines of import statements related to OpenMMLab, such as import MCV, import MZ, import MSEG, etc. In the academic community, OpenMMLab projects are mentioned in more than 1,000 papers. In this CVPR, it is adopted by 76 papers on various topics. Meanwhile, we have seen more than 20 change winners adopting OpenMMLab as their codebase. We can see many big names from all over the world that use OpenMMLab for research or production, such as Google, Microsoft, CMU, etc. Actually, most companies, most big companies and famous universities are using OpenMMLab in their research. Now, I would like to introduce some updates in the past year. Since July of last year, we released 6 new code bases in different areas. They are mSelfSoup for self-supervised learning, mFuture for future learning, mFlow for optic flow estimation, mRotate for rotated object detection, mRazor for model compression, and m3D for 3D human parametric model. We are glad that researchers and teams outside are contributing new projects to OpenMMLab. For example, mHuman 3D and mRotate are maintained by our collaborators. Besides covering more areas in computer vision, another milestone is MDeploy, the model deployment framework. With MDeploy, we can deploy OpenMMLab models to a variety of hardware and devices, like GPU, mobile phones, edge devices. With it, industrial users can easily adopt OpenMMLab in their business for end-to-end solutions. Next, I will briefly introduce the newly released code bases. The first one is self-soup. It implements many popular self-supervised learning paradigms and algorithms, such as pretext task, contrastive learning, and masked image modeling. There are more than 15 algorithms in self-soup, making it the most powerful toolbox for developing self-supervised learning methods. Moreover, we provide rich benchmarks and downstream tasks for evaluating self-supervised models. Due to the unified design of OpenMMLab, users can evaluate the model in object detection, semantic segmentation, post-estimation, and so on, without modifying much code. MFearshot is the first open source codebase that provides unified implementation and evaluation of fearshot learning. Here we show two tasks, fearshot classification and fearshot detection. The toolbox provides strong baselines and state-of-the-art methods in the two tasks. Based on classification and detection, users do not need to write lots of code to implement a new method, and can adapt existing techniques to other classifiers or detectors easily. Optical flow estimation has been studied for a long time, and there are some traditional methods implemented in OpenCV. However, in the deep learning era, there lacks a unified codebase for flow estimation. Thus, we developed MMFlow, the first systematic toolbox for optical flow estimation. It implements classical methods like FlowNet, FlowNet2, and PWCNet, and some newer methods like Raft and GMA. Some methods just release the inference code, and we re-implement the training and achieve comparable or even higher results. We decompose the flow estimation framework into different components and makes it easy and flexible to build a new model by combining different modules. Here is a demo of MFlow. Okay, let's move on. OpenMMLab has supported both 2D and 3D object detection, and now we extend it to the rotated bounding boxes. MMRotate is the most powerful and complete toolbox for rotated object detection. It provides three mainstream angle representations to meet different paper settings. It implements a variety of methods. Many of them are official code released by the authors. And also we can show the demo. Or we can turn on the music. Okay. MS3D is an open source code base for the use of 3D human parametric model in computer vision and computer graphics. Human 3D re-implements popular methods that allow users to reproduce state-of-the-art results with one line of code. It is also convenient for rapid prototyping by simply modifying config files. Well, we also develop a unified data format, human data, to align all supported data sets, which makes data processing more convenient and efficient. And Human 3D also provides a suite of differentiable visualization tools for human parametric model rendering. including path segmentation, depth map, and point clouds, as well as conventional 2D or 3D key points. Now we can show some visualization. Okay, go on. MRazor is a model compression toolkit for model slimming and AutoML, which includes 3 mainstream technologies: neural architecture search, network pruning, and knowledge distillation. We are developing the quantization module, and it will be available in a few months. Due to the similar architecture design of OpenMMLab projects, we decouple the slimming algorithms and vision tasks. And MRazor can be easily applied to various tasks. With better modular design, developers can implement new model compression algorithms with only a few codes, or even by simply modifying config files. Yeah, we have no demo for MRazor. Next, we move to the production. Besides developing more and more toolboxes for research, we step forward to production. From research to production, what we need to do is to deploy the model on specific devices, such as CPU, GPU, mobile phones. When we have developed a novel algorithm and obtained a PyTorch model after training, a general pipeline for model deployment is to first convert it to some intermediate representation, or IR for short. For example, Onyx. And then we convert the IR model to the format accepted by the inference engine on the target device. During this process, we need to resolve some issues like how to convert the model, how to handle the operators that are not supported by the IR or the inference engine. Now we present the architecture of MMDeploy. This is our solution. MMDeploy naturally supports OpenMMLab projects like MMClass, MMDet, MMSeg, etc. It mainly consists of 3 components: model converter, SDK, and backend extension ops. Model converter converts PyTorch models to IR models and IR models to inference engine. SDK provides simple and unified APIs to execute the model, and the users can develop applications based on the SDK. Backend extension ops are a set of operators used by both the model converter and the SDK. We implement lots of operators on different inference engines and devices. There are 4 major advantages of MMDeploy. It supports various inference engines, such as TensorRT, Onyx Runtime, OpenMML, NCNN, LibTouch, etc. And also it supports multiple platforms. MMDeploy is compatible with Linux, Windows, Android, and also we are working on macOS. And also it supports multiple languages. You can program with C or C++, and also Python, Java, or C#. So you can see that most popular languages are supported by MMDeploy. Lastly, MMDeploy provides flexible integration to user systems. Users can choose what to integrate into their own system. For example, they can just adopt the IR model, or they can use the inference engine models, or they can use deploy SDK. And this is a more detailed paragraph. Okay, so we have code bases and we train PyTorch models, and then we use PyTorch to Onyx, PyTorch to TouchScript, and also the Onyx optimizer to convert the PyTorch model to IR model. And then we use Onyx to TensorRT, or Onyx to NCNN, or Onyx to OpenMMLab to convert the Onyx model to backend model. Lastly, we use the SDK to pack the deploy model. Here is an example. For example, we can deploy RetinaNet to the NVIDIA GPUs. Firstly, we use the model converter, just a single line of command. For example, here we provide deploy.py. And then it will convert the RetinaNet PyTorch model to Onyx model. And then we can get the Onyx model and also the TensorRT model. Here it consists of some meta files and the TensorRT engine. Lastly, we can use SDK to run the model. Here we use Python APIs. So we can construct a detector and then use the detector to inference an image. So it's just very simple. Okay, we have introduced lots of OpenMMLab projects, and we say that it's very fancy, it's wonderful, it's perfect. But why? Since some papers may also release codes based on no code base, they just build from scratch. But by adopting OpenMMLab, there are some significant advantages. The first one is united architecture. Users can learn once and use everywhere. Since the architecture and APIs are almost the same for all OpenMMLab code bases, users can implement users can learn one code base and they have no pain in learning other code bases. And also users can implement once and use it everywhere. For example, you can implement a backbone and register it in class and use it for object detection, segmentation, post-estimation with just modifying the config files. The second advantage is united benchmark. OpenMMLab provides fair baselines for academic research. For some research areas, different papers may adopt totally different settings, and we cannot conclude whether the algorithm works or the hyperparameter work. In OpenMMLab projects, we study various training tricks and hyperparameters. And finally, form a unified benchmark for all the methods. And the next advantage is modular design. Users are fast to develop and can try new components in very few codes or just modifying the config files. Lastly, the high quality implementation. OpenMMLab is efficient, and also it can obtain high performance, even higher than the original paper. And also it comes with good code style. You can read it smoothly and fluently. And here are the core design of OpenMMLab. So the first one is registry. It is the basis of modular design. And the second is config. We use config to construct modules. And also we use config to manage experiments. And the third one is runner and hook. Runner and hook can provide unified training interfaces. and also provides customizable pipelines for users. So we can have a brief overview of registry. So registry is actually a mapping from a string to a component or a string to a Python object. So when we use a decorator to register some class in some registry, actually we build a dict mapping from the class name to the class itself. Here we map ResNet, the string ResNet, to the class ResNet. And then we can use build functions and also dict at the config to build the ResNet module. So we can build an instance with custom configs. This is very simple, the idea of registry. And then we can show the config. In OpenMMLab, we support Python files, JSON or YAML files as the config file. Here we just demonstrate the Python files. We can use a Python dict as a config, and it can construct a module like in the right. So it's basically a faster RCN, and we can build the backbone with config dict specifying the type is ResNet, and the neck is FPN, and the RPN head is RPN head, and our head is the standard our head. And the last one is a runner and a hook. So what is runner and hook? We can see an ImageNet example like in the left. We need to write some build functions to construct a model optimizer and train data loader first, and then we use a for loop to run several epochs. And in the for loop, we have another for loop to iterate the data loader to iterate the data loader to feed the data and for the model, and also step the optimizer. So this is the inner loop for the iterations. And we just give an abstraction for the whole process. So the runner is the execution loop and the core logic, such as fetch data and for the model. So we can just wrap some core codes in the model.train step. And also we have two loops, the outer loop for epoch and the inner loop for iteration. In each red, as shown in the figure, the red square, we can execute some custom logics or custom methods. For example, adjust learning rate, or we can update the timer. So these custom logics and facilities, we have an abstraction as hook. So we can see another example. Here, when we have we have more hooks. For example, before run, we can execute a custom hook. And also before train epoch, we can run the disk. We can run the disk sampler hook. It will initialize the sampler and set some seeds. And also, before train iter, we can execute the learning rate updater hook and the iter timer hook. And after the train iter, we run the optimizer hook, iter timer hook, and logger hook. And after the training epoch, we can use the checkpoint hook to save the checkpoint, and also map hook to run the evaluation. And before exit the training process, we have the after run hook. We can do some custom logic here. Okay, so these are the core design of OpenMMLab. Lastly, I will give a quick tour for developers and researchers on how to use OpenMMLab. we use two common cases for illustration. First, we show how to support a new dataset, taking new images for semantic segmentation as an example. Then we demonstrate how to develop a new model and apply it to multiple tasks, taking Swing Transformer, for example. The two examples are also released on GitHub. You may scan the QR code to find out more details. Before we dive into the details, I will propose the general guideline for setting up a project. As best practice, we can separate the dependencies and the project itself. Dependencies like mmcv, mmdat, or mmclass can just be installed with pipe, as other normal Python libraries do. The project can be maintained in an isolated folder. In this way, we decouple the project code with OpenMMLab libraries, making it easier to upgrade the version of dependencies, and there is no need to fork mmdat or mmclass repository. Now, I would introduce a useful tool MIM. MIM serves as the package manager of OpenMMLab. We can use it to install mmcv, mmdat, segmentation. It can infer the environment and the dependencies and download the corresponding pre-built packages automatically. On the other hand, it provides unified entry points for scripts. For example, mim trend mmdat is equivalent to running the trend.py script under mmdat tools. And now we can have a more direct demo. Okay, we can type mim install mmcv4, and it will search the proper pre-built packages and install it without compiling. And also we can type mim install mmclass. It will resolve all the dependencies and install mmclassification. And we can use mim list. It will show we have installed mmcv4 and mmclass and the corresponding versions and source. And also we can use mim train mmclass and some config files and arguments. Yeah, so we can the training started. Okay. So with mim, how to support a new data set? There is generally 4 steps. The first step is process the data set, and it is optional. Yeah, because some data sets are complicated or we need to process it, and other data sets we just need to download and extract it. And the second step is to implement a new class. The class is a dataset class. And then we modify the config file, and finally we can train and test. Okay, let's see how to process the dataset. In the project folder, we can write a script named new images converter.py. So we can implement our logic here to process the downloaded dataset into the right part. Yeah. And then we can implement a new class. Here is a new images dataset.py. So in this file, we can use mseg as a library like PyTorch and Touch Vision. And then we can write a class, new image dataset. It inherits from a custom dataset. And we use a decorator at datasets.register module to register this dataset into the datasets registry. And in the dataset class, we override the load annotations method. Yeah. So this is all we need to do to implement a new dataset. Then we can modify the config files. So here we have many, we can see that there are more than 1 config files because we decompose the whole config file into some basic components. for easier combination without writing duplicated codes. Of course, users can write a whole config file without such pieces. Okay, so in the config file, we just define the data pipeline of the dataset. This is how to process the datasets, or the augmentation, the data pre-processing, etc. And we don't forget to import the datasets or import the module. So making the dataset file imported, making the data file import so that the new image dataset class can be registered. After we finish these steps, we can train or test the model just with mim-train mmseg or mim-test mmseg. Then we will show how to develop a new model. There are 3 steps. The first one is implement the model, and then we modify the config file, and lastly we train and test. This is basically the same with the same as how to implement a new class, how to implement a new data set. So firstly, we just implement the model class. Here we just ignore the default function or the detailed implementation of student transformer. We just write the class here. So we also need to use the decorator to register student transformer into the backbone's registry. Okay. Then we will also modify the config file. So if, we can see that when we are training the image classifier, we just need to specify the backbone as type is student transformer, and also the head is student linear head. Okay, and if we want to use student transformer in mmseg or mmdet, we can specify that the backbone is type equals to mmclass dot student transformer, because the student transformer is registered in the mmclass registries. So we can use it also very in a very simple way, without implementing it in mmdet or mmseg. And finally, we can train the swim mask casting with detection. Yeah, and you can find out more details by scanning the QR code. Okay, that's all the presentations. And here are some resources: our homepage, our GitHub page, and also our Twitter account. Yeah, you are free to scan in these QR codes to get more resources. Okay, thank you. Yeah, return to Wei.
Okay, thanks, Kai. So could you first stop the sharing? Yeah. Okay.
Okay. Maybe we can have a quick Q&A session.
Okay, of course.
Okay, if there are no questions, I will stop sharing and pass the time to the next speaker.
Okay, thanks, Kai. Then let's invite Professor Kevin to discuss about improving video super resolution with enhanced propagation and alignment. So Prof. Kevin is a Nanyang Associate Professor with the School of Computer Science and Engineering at Nanyang Technological University, Singapore. He is also an adjunct associate professor at the Chinese University of Hong Kong. He received his PhD in computer science from the Queen Mary University of London. He is the recipient of the 2019 Nanyang Associate Professorship from the NTU. He is recognized by inclusion in the AI 2000 Most Influential Scholar annual list. His research interests include computer vision and deep learning, with a focus on image and video restoration, enhancement, and manipulation. His journal paper on image super resolution was selected as the most popular article by PAMI in 2016. He serves as an associate editor of IGCV at PAMI. He also served as the area chair of CVPR 2019 and 21, BMVC 2018 and 19, and ECCV 2018. He has co-organized several workshops and challenges at major computer vision conferences. So let's invite Kevin. Yeah.
Thanks, Wei. I would like to share the screen. Okay, 1 second. All right, thanks for the kind introduction. My name is Chen Shloi. I'm from Nanyang Technological University. So good morning to those who are attending the conference in New Orleans, and good night to those who are at the same time zone as me. So I'm from the MMLab of NTU. So my lab has been developing many algorithms for image restoration, video restoration, and enhancement. So our previous algorithms like SRCNN or ESRGAN have been incorporated into a library called MM editing under OpenMMLab. So this library basically contains a number of algorithms for image editing, image enhancement, and restoration. So today I'm going to share some of our research work on improving video super resolution, and basically by using enhanced propagation and alignment. Okay, so basically let's look at what is video super resolution. Maybe most of you know about image super resolution. For video super resolution, it has an additional temporal dimension, and therefore it will be harder than image super resolution. So the goal is whether we can exploit the complementary information from other frames to improve the resolution of current frame. So the key challenge here is to how we can gather the information for the reconstruction, and that would involve how we align frames, which can be misaligned because of the object motion, and how we propagate the information from distant frames to the current frame. And that's the key challenge. And the second challenge is how we can cope with diverse and complex degradation, especially when we want to address real-world scenarios. So this is a typical way that we perform super resolution for videos. In general, you gather a number of frames in a local window, and then you feed it into your network, and then you get the results. So this is a very simple and naive way to perform video super resolution. So most assistant work basically rely on this kind of sliding window framework, whereby you apply a local window, and then you try to restore the frames within the window. So what happened here is that your network couldn't reach distant frames to gather information, because you only have limited extent in your local window. So that's the problem. And to solve that, you could use recurrent framework, where you basically propagate information across the whole video sequence. But that would involve a lot of design choices. For example, how many frames that you need to propagate, and how do you design the propagation component. That remains an open problem in video super resolution. So this is our solution. What we tried to do last year is to examine all these components carefully and systematically, and design a simple backbone that has a good trade-off for performance and efficiency. So what we found out is that in order to perform good video super resolution, you would need effective propagation and alignment. So these propagation and alignment are the two key elements to achieve effective and good performance in video super resolution. So we come up with the framework, which is called basic VSR, And in 2020, also last year, we proposed an improved version of Basic VSR called Basic VSR++, and we participated in the entire competition, and we got 3 champions using this method. And in this conference, we present a paper for Basic VSR++. And the 2 main components that we propose in this paper is a second-order grid propagation that I will explain later, and flow-guided deformable alignment. So these 2 components helped to perform better propagation and frame alignment that helped to achieve very good performance in compared to previous methods. So if you look at the graph here, basically our method last year achieved a very good trade-off in terms of performance compared to UDVR, which is another very popular framework that we proposed in 2019. And the latest method here, the Basic VSR++, basically surpasses all the previous methods in terms of runtime and also restoration quality. And another work that we are going to present in this conference is real Basic VSR. So in this paper, what we want to achieve is to cope with unknown degradations in real scenarios. So the main challenge becomes how we could balance between detailed synthesis and also suppressing artifacts due to unknown degradations. So I will talk about that later. And I will also talk about how we can improve training efficiency when we try to train a video super resolution model. So all these methods, the 3 methods here have been incorporated into ML editing. So you can check the code out there. Okay, first, I will talk about Basic VSR++, basically how we can improve video super resolution with enhanced propagation and alignment. So this is the overview of our model. You can see that we have inputs here. This is the input sequence, and this is the desired output sequence. So at the beginning, we will use some residual blocks to extract shallow features from the input sequence. And then we will have a so-called second-order grid propagation to distribute information back and forth, so that we can combine the informations from different frames for the restoration. And within each block here, we have a component called flow-guided deformable alignment. So this alignment components basically help us to align those misaligned frames so that we can aggregate the information for reconstruction. So this is basically the main idea of our Basic VSR++ framework. Okay, let me first talk about the second order grid propagation. So to enhance the robustness of propagation, what we do is that we relax the assumption of first order Markov property in Basic VSR. So in Basic VSR, basically we only take the previous frames to combine with the features of the current frame for reconstruction. But in Basic VSR++, we allowed an additional connection, basically a second order connection, realizing the second order Markov chain. And with this relaxation, the information can be aggregated from different spatial temporal locations, improving the robustness as well as the effectiveness in occluded and fine regions. And as for grid propagation here, what we did is that instead of propagating the features forward and backward, we do this multiple times back and forth, okay, in an alternating manner. So like, as indicated by this diagram here. And through this propagation, the information from different frames can be revisited and adopted for feature refinement. And compared to our previous model, Basic VSR, which propagate the features only once, the grid propagation over here repeatedly extract information from the entire sequence, and therefore improving the feature expressiveness. And you may argue that, okay, this is more complicated than basic BSR, but thanks to the enhanced propagation and the alignment that I will introduce later, this model actually helps us to save parameters because of the effectiveness. And in fact, this model surpasses our previous model by a significant 0.82 of decibel in PSNR, given the same number of parameters. So the next thing I would like to talk about is flow guide deformable alignment, which is another component that we propose for basic BSR++. And to understand that, then we need to know about deformable convolution for alignment. And this has been adopted in some other previous methods like TDAN or UDVR. So what deformable alignment performs here is that it assumes that we have two frames. One is the reference frame, and another one is its neighboring frame over here. And what it does is that we will concatenate these two frames together, and then after some convolutional layers, we will obtain the offset map, okay, which is shown over here. And then this offset map will be used for the deformable convolution to sample different locations for convolution. And with that, what we get here is that we will get a line frame from this neighboring frame, okay, because of the convolution. So in other words, the neighboring frame is warped to the reference frame at the feature level based on the offset. All right, so this is the typical deformable alignment. And for more complicated design, for example, in UDVR, they introduce a pyramid of deformable alignment to perform a better alignment. So in our basic BSR++, we actually redesigned the whole framework over here. So we found that deformable alignment is effective, but it is unstable for training. So what we try to improve is that why not using optical flow to help the learning of the deformable convolution offset. So in our current framework, what we do is that we will we will get optical flow, okay, using SpineNet, and then we will use optical flow to warp the previous frame. Okay, basically we warp the features to the LR features over here, and we concatenate them together. And this concatenation, after going through some convolution, we will get the residual offset instead of the DCN offset directly. We get the residual offset and add it back to the optical flow, and that will give us the DCN offset. And that DCN offset will be used for DCN block to perform deformable convolution. So the good thing about this framework is that we use optical flow as the base offset, and this base offset helps us to mitigate a lot of burden in our estimation over here. We just need to learn the residual offset for the DCN, and it is the offset learning. And the fact that we only learn a small deviation, okay, this small deviation in this residual offset stabilizes the training. And in addition to that, we also estimate a mask over here, which is attention mask. That helps us to provide the flexibility on masking which features are important and not important when we perform the offset learning. So the whole framework here basically helps the alignment a lot. I will show some results later. So here I show the ablations, and basically the flow guided deformable alignment, the second order propagation and grid propagation, they each bring more than 0.1 decibel of improvement. And all in all, they provide over 0.91 decibel of improvement over the baseline. And here I show some visualization of the result. So without second order, we get a restoration result like this, but with the second order propagation, we get a much sharper result. And here is another example that shows the benefit of grid propagation. So without grid, we get the result like this. And with grid propagation, we get much sharper and better restoration. And this figure shows the benefit of using flow-guided deformable alignment. If you perform alignment by using optical flow to align the two frames over here, if you look at the features are pretty blurred. Okay, so that means they are not well aligned. But if you apply flow-guided deformable alignment, you can see much sharper features when you warp the features of this neighboring frame to reference frame. So that indicates a much better alignment between features. So here are the results. Basically, here we assume some blur input, and this is the restoration result. And you can see that only our method can recover the stripe patterns. And this is another video that shows how we can better recognize or restoring the couplet. All right, so you can find more results in our paper. And what we have done earlier is that we only apply this basic BSR++ on the task of super resolution. But in fact, this framework is generalizable to other restoration tasks, for example, deblurring or denoising. But here we need to make a small make some changes to the framework. So in super resolution, we basically assume that the input size is smaller than the output size. But in other restoration tasks, we have the input size and output size identical. So to basically to suit the framework for this kind of for other restoration tasks, what we did is we downsample the input images with stride convolution if the input size equals to the output size. So this is a very simple modification. And the downsampling factor is selected based on our requirements. So if the downsampling factor is larger, then the frame will be faster. And if the downsampling factor is smaller, then we get better performance, but it can be slower. So here we show the results on basically quantitative results of super resolution. Overall, we get more than 1 decibel improvement on this data set with 4 over previous best method, and get the entire 2021 champion. So you can see that the runtime actually is very competitive compared to existing methods. Yeah, it's very fast. And on other restoration tasks, such as deburring, denoising, and also compressed video enhancement, we also obtain the best results. Yeah, we are carrying the state of the art across many methods. Okay, here we show the qualitative results for deburring and denoising, because this is for super resolution. Yeah. Okay, so basically, in summary, for this in this study, we propose 2 novel components. One is second-order grid propagation that allowed us to propagate features more effectively across long video for restoration. And the second component is flow-guided deformable alignment that allow flexible alignment with motion guidance. And we also extend our framework so that it can work on more video restoration tasks. And this can be done by just introducing a very simple extension, which is strider convolution for efficiency. And we get a state-of-the-art performance on many restoration tasks. Okay, so that's the first work on basic VSR++, and you can try that on MM editing. And the second work, which is also another paper that is accepted in this conference, is we call it real basic VSR. So what we did is that we try to investigate trade-off involved when we try to train a model for real-world video super resolution. So when we say real-world video super resolution, what we meant here is that we do not assume any known kernels or downsampling kernels, and we need to deal with unknown degradations in the wild. Okay, this is a more challenging and more difficult problem compared to non-blind super resolution. Okay, this is totally blind super resolution, and you know that. So it is a hard setting, but the more maybe the overlooked question in this problem is that when we train recurrent networks for this kind of real-world super resolution, it actually requires a lot of computational resources. And there aren't any studies out there to basically examine how we can save, how we can cut those redundancies when we try to train this model. And of course, there is no diverse data set out there for evaluation. And in this study, we try to address these problems. Okay, first thing that we propose in this method is image pre-cleaning. So this is a very important mechanism that is required for real-world super resolution. So our observation is that in non-blind settings, when we use more frames, when we do more propagation, then the results will be better. But in real-world settings, if we propagate frames or propagate features from distant frames, then artifacts are amplified with more frames. So if you look at the examples over here, so if we are dealing with non-blind VSR, where we know the kernels, when you use more frames for propagation, then you get very good results. But under real-world settings, when you use more frames, those artifacts from other frames will be propagated into your current frame and actually hurts the performance. So the reason is that the networks are unable to distinguish the high frequency details from artifacts. So that will exaggerate the artifacts when we use a longer propagation. So that's the problem. So the objective of image pre-cleaning, okay, the cleaning module over here, basically is to suppress the artifacts in the input sequence before we send it to the propagation network. Okay, so this is a very simple idea. So just need to introduce a cleaning module over here. So that will make our framework into two-stage. First, you perform cleaning, and then in the propagation network here, you will perform detailed synthesis. So training the cleaning module is very simple. Basically, you just need to introduce cleaning loss. So in the cleaning loss, you would use a low-resolution ground truth to sort of to train the module. And then the loss can be based on a simple MSC loss. And that works pretty well in practice. And you will find that it's essential for removing artifacts. So if you look at these examples over here, without cleaning loss, you get a result like this. And with the cleaning loss, we get much better results. Okay, and that is the first trade-off, basically how we trade off between the propagation, okay, by using a cleaning module. So in the subsequent trade-off, what we examine is that whether we can make the training faster and more effective. So when we deal with real-world super resolution, real-world video super resolution, we basically need to train the model with a lot of synthetic degradations. Okay, that basically translates to using a longer sequence to train the model, and we also need to use larger batch size to stabilize the training. So if you want to cut down the training time, then you need to use short sequence and small batch size, and that would hurt the performance. So that is a trade-off over here. How to improve the performance yet using short sequence and small batch size. So our approach is like this, okay? It's simple. So instead of feeding the whole sequence, like as in conventional training mechanism, so what we do here, we only feed half of the sequence to the model, to the training process, and flip the sequence so that we can make it longer, okay? We flip the sequence to make it longer, and that would have the same length as in the conventional training process, but now we reduce the CPU load, yeah? And to compensate that, the loss of other frames, what we do here is that we increase the richness of the degradations by introducing different degradations or synthetic degradations to each frame, okay? By using, basically each frame will take different degradations. So that will increase the diversity of the training samples. So that is our final scheme, and it works pretty well. From our study, it can reduce up to 40%, basically increased 40% of training speed, okay, without sacrificing the output quality. So you can see the details numbers here, and you can see that basically the results are still very good. Yeah. Okay, and the third and final trade-off that we study in the paper is about the batch size versus the sequence length. So when you try to do the training, you have two options. So and not bursting the memory. So the first option is to increase the batch size as much as you can, or you can increase the length of the sequence of your training. Basically, the length of the sequence to perform the training. So you cannot do both because you have a limited budget for your memory. So you can either choose one. And our finding shows that you should go for longer sequences rather than larger batch size when you try to perform, when you try to train a video super resolution network, if your resources are limited. And that will give you better performance. Yeah, you can look at the details in our paper. Okay, and lastly, we introduced a video LQ dataset. Basically, we collected a number of 50 low-quality videos from diverse scenes for evaluation. Okay, and you can download the dataset from our website. Yeah, I will skip this part, get better results. Okay, I'll skip this part as well. All right, now you can see with our model, you can restore better, you can get very good results. Despite that, we do not know the degradation. So in summary, to train real-world video super resolution model, it involve various trade-offs, like the detail synthesis and artifact exaggeration, performance versus training time, batch size versus sequence length. And in this paper, we study all these trade-offs and provide an answer. Okay, you can study our paper, and here I provide the links to the code to the respective papers and to our website. Okay, before I end my presentation, I just want to make a short advertisement. We are going to have a workshop called a BP workshop, okay, Mobile Intelligent Photography and Imaging Workshop in conjunction with IEEE 2022. And in this workshop, we organize 5 challenge tracks, okay, that emphasize the integration of novel image sensors and image algorithms. I will show the tracks later. And for this workshop, we also invited a number of very cool academic and industrial speakers to share their work with us. The challenge have started. Okay, we have 5 tracks here. Basically, how like for this one, RGB or top depth completion, and Fury mosaic tracks, and how could you fuse the RGBW sensory information. And that's another track on under display camera image restoration. There are many participants now, but if you're interested, you can still join the competitions. And we gave very good awards and prizes. So the first place will get 1,000 USD, second place 800, and third place 500. Okay, the challenge has started and it's going to end in 20th of July. And we also accept papers. If you have papers, say, I don't know, rejected by ECCV, maybe you can try to submit to our workshop, and the deadline is 8th of August. All right, that's all from my presentation. I'm open for questions. Thank you. Okay, if there aren't any questions, then I will pass it back to the session chair. Thank you.
Thanks, Prof. Kevin. Then let's invite Dr. Han Hu. So Han Hu is currently a principal researcher in Microsoft Research Azure and an adjunct PhD advisor at Xi'an Jiaotong University. His main research interests include visual architecture design, self-supervised representation learning, and visual language representation learning. His paper, Swing Transformer, won the ICCV 2021 Best Paper Award and is now widely used in academia and industry. He received his PhD and bachelor's degree from Tsinghua University in 2014 and 2008, respectively. His PhD dissertation received the Excellent Doctoral Dissertation Award of Chinese Association of Artificial Intelligence. He visited the University of Pennsylvania for half a year in 2012 and worked in Institute of Deep Learning, Baidu Research, between 2014 and 2016. He served as an area chair for CVPR 2021 and 2022. So, are you there?
Yes.
Dr. Han Hu. Okay, yeah, I'll stop share.
Can you see my screen?
Yes.
Okay, thank you, Wen. Hi, everyone. I'm Han Hu from Microsoft Research Asia. The title of this talk is Convergence of Architectures and Learning Methods in Computer Vision with Other AI Fields. The goal of AI is to make computers as intelligent as the human brains, or even beyond. So let's first look at the human brain. This is an illustration of the human brain, and this wrinkled part is called the neocortex. It's responsible for most of our human intelligence, including visual, auditory, language, motor, gustatory, consciousness, and so on. Although it has many different functional areas, they are very uniform in structure. By unfolding the neocortex, its shape and size are like a dinner tissue, about 40 centimeters long, and 50 centimeters wide, and 2.5 millimeters thick. Its vertical neural structure is almost identical. Almost all places have 6 layers according to 3 types of staining methods. That is, all these very different abilities, as we mentioned earlier, are implemented using a single neural structure. In fact, this is right a key to the success of human beings, that human beings can quickly adapt to new capabilities and environments. Here is an interesting finding published 20 years ago in a Nature magazine. Please see the left figure. This is a mouse brain. The blue arrows are the neuron paths of how the visual signals are processed. The red arrow are the neuron paths of how the audio signals are processed. The scientists revealed the neuron path as the red figure, such that both the auditory and the visual cortices received the visual signals. After training, the scientists found that auditory cortex can also process visual signals. This experiment indicates that the same cortices can be used for different human abilities. Neural architecture is innate. It requires nurture to work out different capabilities, which correspond to what learning acts in artificial intelligence. Now, the learning methods are also believed to be universal. I studied by Ina Kuhn's famous cake analogy. So in this analogy, different learning methods are mapped to parts of a cake. For example, he thought reinforcement learning is like the cherry. It's very shiny, but the learning signal is too sparse. Then supervised learning is like the icing, which is sweet, but it contains no bit information. So he bet on self-service learning. He thought self-service learning is like cake genoise, which should be the most fundamental learning paradigm to drive the learning of a network. In fact, what inspired Ina Kuhn is the learning mechanism of a baby. Our baby learns to perceive the world through observation by either the sight, the hearing, the touch, and so on. Observations contain rich data, and through some self-supervised learning tasks and this rich data, our brains are learning all the time and helps the brain to possess strong perception abilities. The recent study in brain science has suggested that predictive learning may be one of the most fundamental steps of learning paths for human beings to build their perception abilities. Predictive learning trains the network through comparing the difference between prediction and the actual pictures that appear later. In fact, we live in a world of space and time. Our brains are always predicting what the next moment is. For example, predicting what the picture of a different viewpoint is after our eye movement. Here shows an illustration. The pink part represents the past, and the light blue indicates the future. And we can learn our visual system by predicting the light green part. A further question is how exactly predictive learning is conducted inside a brain. Now, it's believed that the thalamus plays a key role. Please see this figure. It shows an example of visual perception. So starting from the retina, the transmission of nerves will first reach thalamus, and then it will further reach the cortex. And it make predictions when going back to thalamus. So in this way, they can drive the learning by the difference between the prediction and the real picture of the next moment. And beyond the vision, other senses also share similar learning mechanism, including hearing and touching. After talking about human brains, let's turn to artificial intelligence, particularly the computer vision field. We first talk about AI architectures. The past 2 years of computer vision was so exciting that we were ongoing architectural convergence in computer vision with natural language processing. 2 years ago, the mainstream architectures in different AI fields were largely different. In computer vision, convolutional neural network had been the dominant architecture for 30 years. In NLP, Transformer has been a dominant actually since 2017. In social computing, the mainstream architecture was graph network. Now, let's review the evolution of mainstream architectures in two major AI fields, natural language processing and computer vision. Firstly, language and sequential data such as speech recognition. The most popular early architecture was LSTM. It's complex in design, using 4 gates to elaborate gradient explosions and the inability to transmit information over long distances. Until 2013, the revolutionary accuracy improvement in speech recognition is still built by LSTM. In 2014, Google's GRU model simplified the design of LSTM to have only 1 gate, while being similarly accurate in the machine translation problem. The next big architecture upgrade was in 2015, where RNN and attention are combined together to implement machine translation. RNN is used to encode a single language, and attention is used to model relationship between 2 languages. Then we all know that transformer appeared in 2017, and it then becomes mainstream. Then let's look at the field of computer vision. Unlike NLP, we have been always using networks that are built by convolution layers. Convolution was first proposed in 1980s. Applied the convolution networks to a handwritten digital recognition problem when he worked at Bell Labs. It was one of the earliest practical systems in computer vision. In the age of deep learning, the AlexNet, GoogleNet, WGNet, ResNet, and DanceNet, they are all built on convolution layers. It's natural to ask whether NLP and CV can use the same architecture. One way is to apply the mainstream architectures in computer vision to the field of natural language processing. We have known the current dominant architecture in NLP is Transformer, which was proposed in 2017. Almost at the same time, in May 2017, there was a work from Facebook to use convolution to solve the same machine translation problem. The network is named convolutional sequence-to-sequence. The performance was also very impressive, and it achieved SOTA in machine translation at night time. And it also changed the machine translation model from sequential to parallel in training. 1 month later, so we know a transformer appeared on archive, and which achieved higher accuracy, and it was also built by a more elegant building component attention. Then everybody's attention was on transformers. And however, there are also some works continuously exploring convolution in NLP. For example, dynamic convolution in early 2019, and deformer convolution from our team. But unfortunately, they didn't become mainstream because transformers are so is continuously improved, and it can be combined well with BOT or GPT. So for now, transformer is still the dominant architecture in NLP. The other way is to adapt the mainstream architecture in NLP to computer vision. After several years continuous exploration, this road gained great attention, represented by 2 works. One is VIT from Google, and the other is Swing Transformer. Swing Transformer for the first time surpassed all previous CM methods by a large margin, and 2 visual benchmarks. One is local detection, which is a region level task that predicts location and categories of objects. Here are the best methods across EOS and COCO. Before Swing Transformer, all methods are based on a same backbone. Now Transformer backbone has taken over on its benchmark, starting from a swing transformer. Here is another benchmark called IEEE 20K segmentation, which is a pixel level task by labeling the category of every pixel. Also, in previous years, all methods are based on same backbone. Now, our transformer architecture becomes better. In particular, swing transformer surpassed the previous best method by 3.3. Since then, transformers took over more and more benchmarks in computer vision. Also note that although it was until 1 year ago that transformers started to take over CNN on various computer vision problems, the journey that applied attention layers for computer vision problems began soon after transformer was proposed in NLP. In November 2017, there were 2 popular works that apply attention layers to vision problems, including non-local neural network and the relation networks. The former uses self-attention modules to encode the global dependency between pixels, while the latter builds relationship between objects, which result in the first end-to-end object detector. In April 2019, we developed local relation networks, which was the first full attention wish backbone. In fact, we have long believed that self-attention or transformers can act a universal architecture for different AI domains. Our belief comes from 2 reasons. Firstly, transformers can be treated as a general graph, where all concepts and their relationship can be modeled by a graph. The concepts can be either concrete or abstract. This general modeling capability is also partly attributed to the verification principle in building relationships between graph nodes. Please see the right illustration. No matter how different the input is, for example, the image patches in different scales, or the multimodal input such as text and image patches, their relationship can be all modeled by verification in an embedding space. This general capability enables transformers to model all kinds of relationships in computer vision, such as pixel-to-pixel, object-to-pixel, and object-to-object relationship, which almost cover all vision applications. During the last 5 years, our team has conducted a lot of research regarding these 3 kinds of visual relationship. I will briefly introduce 4 of them, highlighted in red. The first work was relation networks for object detection, which was published on CVPR 2018. This work aims to model the relationship between objects. Please see this image patch. It's rather different. It's not easy to figure out what it is by seeing this patch alone. However, if you stay in the context, it's easy to recognize a patch as a baseball glove after noting that a baseball player is holding it. This module helps to create the first fully end-to-end object detector. This self-attention module can be inserted into 2 steps of the fast RCN detector. Please see the red blocks in this pipeline. Firstly, it's inserted in the instance regulation head. Now, given this module, the objects can be jointly recognized instead of processed separately as in previous methods. The second is to do duplicate removal. In previous methods, duplicate removal is usually achieved by a handcrafted non-maximum separation method. By the self-attention module, we can make this step end-to-end learnable. So we came up with the first fully end-to-end object detector. Now end-to-end detection has been a common practice due to a follow-up famous paper named DTR, published on ECV 2020. One key of this paper to achieve end-to-end detection is also the attention module. The second work I would like to briefly introduce is local relation networks, published in IEEE 2019. Its motivation is from a criticism of the convolution layer. In fact, the convolution layer is criticized to have low efficiency. Convolution performs a template matching using a fixed filters across all image positions. So please see this image. There are 3 boards with slightly different head poses. With the convolution layer, we need 3 channels to encode these 3 board heads, which is inefficient. Other than using fixed filters across image positions, transformer layer can use adaptive filters across positions. And in this way, potentially, we need only 1 channel to model different board head poses. By self-attention layers, we developed the first fully attention visual backbone. It's achieved by replacing all convolution layers in the ResNet with transformer layers, maintaining the same computation complexity. The network is named Local Relation Networks, LRNet for short. This curve shows comparison of this network with ResNet and IMNet 1000 calculation. The blue curve shows the result of ResNet with increasing kernel size, which is based on convolution layers. The orange curve shows the result of our local relation networks. The transformer-based local relation network is 2.7% better than ResNet. However, this network is not practical at that time due to slow inference speed. I will introduce swing later, which address this problem. Another well-known work was vanilla Vision transformer, which directly applies the standard transformer used in NLP to the problem of computer vision. Please see this illustration on the right. The vanilla Vision transformer partitions an image into small patches and directly applies a transformer on these patches to output a class label. So it's very straightforward, and also it has demonstrated very good accuracy on image classification. We argue that this vanilla vision transformer doesn't consider the key difference between visual and text signals. First, a visual object can be in different scales, which advocates a hierarchical structure in architecture design. A fluffy cat is a fluffy cat, no matter how large it is. But for a sentence, the words or tokens have no scale variation. We cannot say, I am a fluffy cat. This is invalid in grammar. Second, the visual signals are usually smooth in space. For example, these 2 grass patches have similar texture, and they are both colored green. This property encourages locality prior. In contrast, there is no spatial smoothness in a sentence. Thirdly, a visual object can be in different locations, which advocates translation invariance in architecture design. A fluffy cat is a fluffy cat, no matter where it is in an image. In contrast, a word is sensitive to its location. It has different part of speech when appearing at different locations. By using these computer vision priors, we can build a bridge from the standard transformer architecture in NLP to that in computer vision. This is an illustration of the standard transformer architecture in NLP. We can say it's plain with a similar solution at the different layers. It computes the relationship among all words globally at each layer. It also accounts for absolute positions of each word in computation. So to build a bridge to computer vision, we introduce priors of hierarchy, locality, and translation invariance into the transformer architecture. And as a result, we came up with swing transformer, which performs strong various vision problems. An important technical innovation of swing transformer is a shifted window approach. This design ensures our faster speed in real computation, particularly when compared to the traditional standing window approach. used in our previous work of local regional networks. So in the previous standing window approach, information was collected between neighboring pixels. That is, each pixel is centered on itself and takes a neighborhood window for calculation. To improve speed out, we propose a design that doesn't overlap the windows. So you can say the non-overlapping windows in layer L. And to exchange information across different windows, we propose in layer L+1, we shift the window configuration by half a window so that the information in the previous layer can be exchanged between different windows. So what is next? Given that the basic modeling of configuration is shifting from CNN to transformers, we believe that this is just a start, and then there is a long road in the front. So one important question to answer is whether vision models can benefit from scale up like that in NLP, because this is the most successful findings in NLP during the last 3 years. To answer this question, we trained a 3 billion parameter dense vision model, which is the world's largest and most effective vision model. Unlike previous billion scale vision models, which were only applied to the image classification problems, our model can be applied to broader visual tasks, such as object detection and semantic segmentation, which requires much higher resolution. It also reduces the requirements on very large label datasets, such as GPT 3 billion. GPT 3 billion has 3 billion images, and we only rely on 70 million images. The new model is named CVPR'22G, and it set new records on four vision benchmarks, including IMNet 1000 V2, COCO detection, ADE 20K segmentation, and kinetics 400 action regulation. Also note that although CVPR'22 has made one step forward, the visual models are still far smaller than that of NLP models. We can look at these curves. The gray curve represents the change in the size of NLP models, and the green curve represents the change in the size of vision models. We can say the gap is about 200 times, and the gap with the human brain is even larger. It's about 50,000 times. So the vision models still have a long way to go. As has been shown effective in both fields of natural language processing and computer vision, we expect transformer could be generic to arbitrary signals or domains, including social computing and AI for science. So swing transformer actually shows an example of how to apply transformers in a specific domain. Concretely, it can be recognized as a combination of generic transformer and several domain-specific pairs. The domain-specific pairs can be encoded by the existence of edges in a graph. This formula of generic transformer unit combining domain-specific pairs can be also set as a principle to guide architecture design in social computing or AI for science. For example, by this principle, graph former won a competition which predicts the quantum property of molecular graphs. After talking about architectures, now we turn to learning methods. For learning, we are mainly concerned about the pre-training, which is now a common practice as a first step for model training. Like architectures, the pre-training methods of different AI fields had been also different for a long time. For computer vision, supervised learning on IMNet 1000 had been a standard approach for a long time, whose goal is to classify the images into 1000 classes. For natural language processing, please see the figure on the right, the mainstream method is language modeling, such as BERT-based method, which is based on math language modeling. And let's look at a more detailed block diagram of BERT. On the left is the pre-training step, where parts of the sentence are masked in the input section. And the goal of the network is to predict the token ID of those masked parts. Once it is pre-trained, it can be fine-tuned for a wide range of NLP tasks. We have known BERT is a milestone, and since BERT, almost all NLP tasks have been using transformer architecture and BERT or GPT-like pre-training methods. At the same time, in computer vision, although supervised pre-training approach has been the mainstream for a long time, there have been also many works exploring self-supervised pre-training. In fact, the pioneer work of autoencoder is a self-supervised approach. It has largely triggered the emergence of deep learning in computer vision. Here is a summary slide about self-supervised learning by Andrew Zisman a few years ago. Please look at the approach in the circle. It has been very close to the masked language modeling approach used in BERT. Yeah, this task is called imprinting. After many years continuous exploration, in 2020, there was a renaissance of self-supervised learning in computer vision, represented by MOCO, which is based on contrastive learning. And it, for the first time, surpassed the supervised approaches on 7 downstream tasks. Our team has also proposed an approach based on contrastive learning named PISPRO, and it's inspired by eye movements. We know the human eyes can usually move 3 to 4 times in 1 second. In fact, the picture presented on the retina changes greatly when the eye moves. But why don't we feel dizzy? This is because our brain is continuously predicting the picture after eye movement, so that when the new picture enters the retina, we will feel smooth. This is right the main idea behind the PISPRO. So for image, we train the networks to have to make the features at the intersection of 2 cropped image views to be close to each other. The PISPRO approach is not built by prediction, but by comparison. Recently, there is a big trend in the field of computer vision that to use GPT-like or bot-like method for self-supervised pre-training. And many methods have been proposed, including ImageGPT, BAIT, SimMem, MAE, PICO, data to vector, and CAE method. Please look at the right, which shows SimMem from our group and MAE from Meta. The methods are very simple. So for each image, we mask a large portion of image patches and train the vision network to predict these missing values. And so the model is pre-trained. These approaches are called masked image modeling. Regarding its strong connection to masked language modeling like BERT, it deserves carefully examining the difference of vision and language signals so as to make it work well for computer vision. So let's first look at the NLP and the training task and left, where we will mask the word fluffy. The goal of learning is to recover this word. We also notice that the text has no spatial smoothness and the text tokens are semantically high level and discrete. In contrast, please see the right. The image is highly coordinated in space and the signal is raw, continuous, and low level. Regarding these differences, we choose to use a much larger portion of masking area, for example, 60%, instead of a small ratio of 15%. This adjustment to use a large portion of masking area and a large patch size, for example, 32, was a key to the effectiveness of SimMem. In the end, there is a single message to take home, that computer vision in the past 2 years have experienced architecture and learning convergence with natural language processing and other AI fields. In architectures, transformers have been the mainstream architectures for both NLP and CV. In learning, predicting unknown input has been important pre-text task for both NLP and CV. So it has been a year to embrace converged architectures and learning methods in artificial intelligence. Finally, I would like to thank OpenMMLab. Our study actually heavily relies on this great project. In fact, we directly use the MM detection, MM segmentation, and MM action tool for the development of swing transformer for object detection, segmentation, and action regulation. So thanks OpenMMLab and thank you all for your attention. Thank you.
Okay. Thanks, Dr. Han Hu, for today's sharing. Let's invite Professor Han Zhao. So Han Zhao is currently an assistant professor at the Institute for Interdisciplinary Information Science of Tsinghua University. He's also a principal investigator of the Mars Lab. His research interests multimodal machine learning, autonomous driving, and computer vision. He was a research scientist at Waymo. He got his PhD degree at MIT under Professor Antonio Torralba, and his master under Professor Ramesh Raskar. Before MIT, he received his bachelor degree from the CKC Honors College, Zhejiang University. So let's welcome Professor Han Zhao. So are you ready? Yeah.
Cool. Can you hear me?
Yes, can hear you. Yeah.
Okay.
You can share your screen now. Yeah.
Okay, sounds good. One second. Okay, cool. Yep, I'm very honored to be here to present remotely to everyone, and hopefully next year we have a chance to meet in person. First, about myself, as introduced, I'm an assistant professor at Tsinghua University, and leading a group called Mars Lab. But of course, our Mars Lab is not limited to working on autonomous driving problems. We also work on a series of interesting and challenging AI problems like multimodal learning, robotics, novel sensors, and etc. If you're interested, please visit our website. And in the past 2 years, we have been actively working on the topic that we called vision-centric autonomous driving, VCAT. And we have published or released a series of papers on this topic. That's what I'm going to talk about today: Deter 3D, Filter 3D, Muter 3D, HD MapNet, Vector MapNet. If you're interested, you can also visit our big project website, vcatai.github.io. Okay, now let's move to the problem of VCAT. The first question that may come up to your mind is why vision-centric autonomous driving? Actually, in the past decade, if you are very familiar with self-driving problems, most of the solutions are heavily reliant on LiDARs and HD maps. For example, we use LiDARs to measure the distance of ourselves from the obstacles. We use LiDARs to build a prior point cloud map to know about the world beforehand, before we drive. And we also use LiDARs to locate ourselves, to do localization in the map so that we can use the prior map for driving. So in comparison, vision is very underexplored. However, as we know, vision contains rich attributes beyond geometry. For example, if we look at this example, from this picture, we can see that what we can see is that the road is under construction and one lane is blocked by the orange cones. And the construction workers and the vehicles are doing some constructions in that area. And one construction worker is waving to us, telling us stop and telling us to detour. This road is blocked, right? We can tell a lot of information from this picture, but it's almost impossible for you to tell from a LiDAR scans. So vision can provide us with this holistic scene understanding and help us make better decisions during the driving. The second reason about using vision-centric autonomous driving is because vision is very scalable. The scalability of vision is almost non-replaceable by LiDARs or radars. Compared to LiDARs, vision is very affordable for all kinds of vehicles. For example, the delivery robots, like the robo-taxis and the robo-trucks, right? The cameras are only like $100 or even or even 20 to within $100. And what is more important is that vision has mature protocols for data collection, data compression, and transmission. So we can expect that more visual data being used in machine learning in the long run. Finally, vision-centric autonomous driving does not mean that we will do vision-only autonomous driving. I personally believe that sensor fusion is critical for the safety of self-driving vehicles. So we should work on vision-centric sensor fusion technologies as well. Okay, then the second question that you may have about VCAT is that how is it different from 2D computer vision tasks? Here's an example that we call it perspective perception. Our input of the model is a picture, and we go through like a UNet, like encoder-decoder model, and finally get a prediction of its segmentations. When we say segmentation, that is the per pixel prediction of its labels. For example, a car on the left will be parsed as a car label on the right. It has a 1 pixel to 1 pixel mapping. And for another car, we can also find its labels in the same position in the output corresponding to the input. However, in autonomous driving, we do everything in 3D. Sometimes we also call it BV space, bird's eye view space. That is, we do not really care how the results in the image plane, but we care about how the object sits in the 3D world. In this example, the bus on the left will be parsed to the position on the top left corner of this BV segmentation map. So this BV segmentation map is viewed from the top to down. So it looks a little bit weird. It looks like a trapezoid, right? And say there's another car that is further away, and it will be parsed into a position on the top borders of the output segmentation mask. And as we can see, it's really hard to find the one-to-one correspondence between the input and the output. And most of the time, 1 pixel in the input image corresponds to an array in the 3D space, which makes things really complicated. It's no longer a one-to-one mapping anymore. Okay, so our work on VCAT tries to solve this challenging problem. The inputs of VCAT mostly are surround view images from the surround cameras on the vehicles. And one series of work, there are 2 projects, one project called HDMapNet and another called VectorMapNet, tries to parse the static map elements around our vehicle from the bird's eye view, basically from the top, right? Our cameras are viewed from the surroundings. And however, our results are from the top. And another series of work, we have 3 projects that are called Deter 3D, Filter 3D, and the Muter 3D, tries to parse the dynamic objects around the vehicle. So whenever we have the static map elements and also have the dynamic objects, we're able to do the downstream task for self-driving, for example, prediction and planning. So today I will give an overview of all these 5 projects. So the first one is called DETER'22, 3D object detection from multi-view images via 3D to 2D queries. This problem, the 3D detection problem from images, is fundamentally a molecular 3D detection problem, which has been there for a long time. And traditionally, people use pseudo LiDAR technology to predict depths for each pixel. And then after we have the depths for each pixel, we have a pseudo 3D point clouds. So that's why it is called pseudo LiDAR. And then we can perform 3D detection on the point clouds with some 3D methods. For example, like point net, point pillars. However, such methods requires additional supervision for the image pixels, right? And also it is actually a 2-stage method. So it will bring us some corresponding errors. If the depth prediction is not accurate, and then our 3D detection will not be accurate as well. Then we can talk about the advantages of DETER'22. This is a method that we perform detection in 3D space, even though the observations are 2D. However, we do not reconstruct the 3D space explicitly, like pseudo LiDAR. And a third, it avoids post-processing like NMS. So this is a fully differentiable, fully end-to-end method to do 3D detection from 2D images. Now let's dive into the model architecture. First, for the input of the model are the surrounding images from surround view cameras. For each image, we send it into a camera backbone like ResNet to extract their features. And then the key ingredient of our model is the query from 3D to 2D, our geometric correspondence. The idea is that we first initialize a query, and it goes through the transformer decoder to decode into a predicted 3D bounding boxes, into a 3D bounding box. And then we take its center as the 3D reference point. And then we rely on camera intrinsic and extrinsic to project the 3D reference point onto the 2D image features, and then extract the features and combine it with the positional encoding, the positional embedding, and finally send back to our transformer decoder. And we'll do it multiple times so that basically this module, the query from 3D to 2D module, will learn where the objects are in 3D. And in the whole process, we only do 3D to 2D projection and no 2D to 3D projection. So the problem is well posed. Please mind the difference between our method and the pseudo LiDAR, right? Pseudo LiDAR predicts depths for each pixel. So this is a 2D to 3D thing, which is very challenging and ill posed. Our approach is well posed in comparison. And finally, the computation of loss is very similar to DETER. We have a bunch of predicted 3D bounding boxes, and we do Hungarian matching with the predictions and the ground truth. And finally, to do the back propagation and the model optimization. And DETER'22 achieves really nice results on the new things benchmark. And around October last year, we got the first place on the benchmark. And the next project I'm going to talk about is Filter'3D, a unified sensor fusion framework for 3D detection. This is a direct extension of DETER'3D. That's why I put them together. Let's look back on some previous work on LiDAR camera fusion for autonomous driving. I can see like 2 streams of work. One stream is based on, is more like rely on LiDAR. It's basically they propose objects from the LiDAR sensors, from the LiDAR data, and then refine these boxes with the cameras. And the most representative work is this one, multi-view 3D object detection network for autonomous driving. And another line of work rely more on cameras. For example, this paper called Frustum point nets for 3D object detection for RGBD data. The idea is that we propose objects from image data only, and then refine them according to the LiDAR data that is within this frustum based on the 2D detection box. So in our work, we ask, is there a simple unified framework that is agnostic to sensor types? As we can see, all these related works assumes that we can do some proposals based on one type of sensors and then refine on the other. However, what if we have some other types of sensors? Is there a unified framework that is easy enough to adapt to multiple combinations or different combinations of sensors? As you can see on the left, I list multiple sensors like 3D radars, low resolution LiDARs, high resolution LiDARs, 2D cameras, and even 4D imaging radars. We designed this model, this framework, in the hope that these different combinations of sensors can serve different types of vehicles, from robotaxis, from consumer vehicles, from trucks to delivery robots. The answer is still the 3D object queries that's proposed in DETR3D. So a quick look back on the model architecture of DETR3D. We have image backbones, and we have a 3D reference point that will extract features from the image feature maps and combine them in 3D, combine with positional embeddings in 3D and send to the transformer decoder, and finally predict the 3D bounding boxes. So the only addition to the filter 3D is that now the 3D reference point can support multiple types of sensors. It can not only extract features from cameras, it can also extract features from radars and LiDARs. As we can see, the LiDAR data are originally, they sit in 3D. So the 3D reference point can directly extract features from them if the data is in, say, in the voxelized 3D space. For the radars, most of the radars are 2D. So basically you can only detect objects on the road surface. You don't know the height of this object. Then the 3D reference point can do the same from 3D to 2D, according to 3D to 2D correspondence, and extract the features in like a pillars, in a pillar way, right? The radar data are like pillars, and the 3D reference point will project onto these pillars and extract them. The decoding process are the same as the DETR3D. Here are some qualitative results of this filter 3D model. We find some interesting examples. For example, on the left is the result from a 4-beam LiDAR plus the cameras. And on the right is the result from the 32-beam LiDAR. We see that in the 4-beam LiDAR case, we can detect very distant objects, while in the 32-beam LiDARs, we cannot. The reason is that most of the LiDARs, the commercial LiDARs today, can only see as far as 100 meters. If beyond that scope, and we can only use cameras to help us to detect the small and distant objects. Here is another case of we comparing 4-beam LiDAR plus cameras, the fusion case, and the pure LiDAR, 32-beam LiDAR case. we see that the cameras help us better detect objects, detect some weird objects or out of distribution objects. In this example, the pure LiDAR model detects this garbage bag as bicycles. However, in the 4-beam LiDAR plus camera fusion case, it will not be misdetected. It will not be detected as bicycles. As we compare these a bunch of different results, we find one interesting quantitative result is that we found that if we use Filter 3D, a 4-beam LiDAR plus camera can achieve a competitive performance with a 32-beam LiDAR. And as you may know, the 32-beam LiDAR is way more expensive than the 4-beam LiDAR plus cameras, right? So that said, the Filter 3D model enables low-cost solutions for autonomous driving. And the next project, also very related to Deter 3D, is called Muter 3D, a multi-camera tracking framework where 3D to 2D queries. There are a lot of works on object tracking using traditional Kalman filters, and also Kalman filters offers strong performance. And there are also some recent works on learning-based associations for tracking. However, here we are seeking a more end-to-end, fully differentiable framework for 3D object tracking. And that's why we proposed Muter 3D. Muter 3D is based on Deter 3D. We use a query-based approach to perform detection and tracking jointly. Most importantly, we achieved the implicit association within the framework. As you can see from this figure, on the left is the tracking at t equals to 0, and we initialize a bunch of queries to detect the objects within that frame. So at t equals to 0, this is exactly the same as object detection with Deter 3D. And then when objects are detected, we'll throw away some queries that have not detected. Each query can capture one object, and we will throw away some queries that do not contain objects. And we'll keep the queries that contain objects to the next time frame. And then at t equals to 1, we have some old queries, and we also sending some newborn queries so that we can capture some new coming objects. And then we do the same way as Deter 3D for object detection, and we'll throw away some queries that do not contain objects as dead queries. And then we'll send the queries that contain objects to the next frame. And in this way, we achieve a fully end-to-end implicit association tracking model. Muter 3D achieves very competitive performance on the NewSync benchmark, and it got the first place in early this year. Okay, that's all the things about object detection and tracking. And then for the next part, I'm going to talk more about how we understand the road, how we understand the map of our environment in our environments. The first work is called HDMapNet, an online HDMap construction and evaluation framework. It was published in last year's CVPR workshop and ICRA. Classical pipelines of annotating and maintaining HD maps involves a very complex pipeline, and it's very costly and labor intensive. Moreover, the road conditions are changing, right? And so if we want to use an HD map for long term, it requires maintenance and updates. So in this work, we want an online method that takes camera images and maybe LiDAR as well as input, and use a neural network to directly output vectorized BV HD semantic map. Here's a short demo for HD MapNet. On the left are the input surround view images, and on the right are the predicted map results. The red lines indicate lane boundaries, the white ones indicate the dividers, and the yellow ones indicate pedestrian crossings. We align the LiDAR point clouds just for visualization. This is not used as input. Due to the limited time, I'll just quickly go through the model architecture for HD MapNet. The basic idea is that we have input surrounding camera images, and when the images go through a camera encoder, and then they will be projected onto a BV space, BV feature space. And if we have LiDAR, we can also encode the LiDAR signals, the LiDAR point clouds with point pillars, and also encode them in the BV space. So, and after they are concatenated in the BV feature space, we'll decode the feature maps. The decoding outputs are three maps. One is semantic mask, and the second one is instance embedding. We'll combine the semantic mask and the instance embedding to obtain the instance mask. And the third output is the direction maps. And then combined with the instance mask, we combine the instance mask and direction with non-maximum suppression and do some connection and post-processing. We'll finally get a vectorized HD semantic map as shown on the right. Here are more qualitative results. We can see that the HD MapNet can accurately predict the road boundaries, road lane markings, crosswalks very nicely, right? We also conduct some temporal map aggregation. And this is a very exciting results that I like. As you can see, our car, we didn't enjoy it here, but the car is driving onto the bottom right, towards the bottom right. And we can see the map gradually growing, right? And that means we have seen more of the map and we have a better understanding of the map and we can plot a bigger map over time. Okay, after we have the HD MapNet, we are considering another problem. The HD MapNet model architecture looks really complicated. It's basically a combination of a BV segmentation task together with some post-processing to finally get the map that we really want. When we talk about map, they are vectorized because we really need to know each lane marking. We don't want the segmentation as our pixelized segmentation as our output, but we want instance-wise lane markings. We know which lane markings are we driving close to, which traffic lights we're attending to, and how many stop signs are there, right? We need the instance level information. That's why we really want a vectorized map. Then the question is, do we have an end-to-end solution to directly produce the instance-wise or the vectorized maps directly? Yes, the answer is yes. We have HD MapNet 2.0. It is called Vector MapNet, end-to-end vectorized HD map learning. As I said, the high-level idea is that we have sensor data input, and we want to directly get vectorized map as output, with everything including like the lane boundaries, the pedestrian crossings, dividers, and etc. Right? And in this black box in the middle, we want to do several things. First, we want to do BV projection, as we did in HD MapNet. And the second, we want to do the map element detection and regression. How do we achieve that? The answer is transformers, just like DTR'3D. We pose it as a detection problem so that we can solve it with the DTR or DTR'3D. And our second novelty is that we use polyline as the primitive for traffic elements. Because polyline is a very nice representation or primitive for the geometries. For example, we can use polylines to represent a line. We can use it to represent a curve, like basically a sampled curve, right? We can also use it to represent a polygon. Polygon is a closed polyline. We can also use it to represent points like stop signs, traffic lights, and so on. And finally, we solve the problem in a detailed way. Due to the limitation of time, I will not go into the details of this model architecture, but the basic idea is that we split the model into 3 stages. First, the BV feature map projection. And second is called map element detector. So we pose it a detection problem. And thirdly, we will try to, the third stage is called polyline generator. And finally, to generate the geometry of each polyline. Let's take a quick look at the qualitative results of vector map net. The vector map net results here is on the rightmost column. And compared to other results, as you can expect, because we represent everything in polylines, so the lines will be straight, right? Compared to pixelized or segmentation-based methods. Secondly, vector map net can also capture some details that are missed in other methods. And also we notice that sometimes in HD MapNet, we will get some loopy lines. And in vector MapNet, we never see such kind of results. And also, surprisingly, in the data set, we found that there are some mislabeled lanes, mislabeled lane crossings, pedestrian crossings, sorry. And that is captured by our vector MapNet. Okay, finally, I would like to, I think that's all about our work. And finally, I would like to acknowledge or thank all my collaborators and the students who work really hard for this, this joint goal of vision-centric autonomous driving. And I would also like to thank OpenMMLab for their very nice toolbox. Most importantly, we heavily use MM detection 3D, which also spurs a lot of impactful works. Apart from ours, there are also other works called Focus 3D, BEV Former, Transfusion, BEV Fusion, and etc. So I encourage all the audience and try their MM detection 3D toolbox. It helps a lot. Thank you. That's all my presentation today.
Okay, thanks, Prof. Han Zhao. Thanks for the wonderful sharing about the autonomous driving techniques. Finally, let's invite Haodong. Let me share the screen. Yeah. Wait a moment. Yeah. Haodong is currently a third-year PhD student at MultiMedia CHK, supervised by Prof. Dahua Lin. His research interests are video recognition and human-centric action understanding. Before that, he received his bachelor degree from Yuanpei College, Peking University. He is also a main contributor to OpenMMLab. So let's welcome Haodong.
Okay, so hello everyone, and my name is Haodong Duan, and I'm a third-year PhD student at Multimedia Lab CHK. My talk today is about action recognition in a human-centric view, and in this talk I will share some research projects on this topic. Yeah. Okay, let's first look at the definition of action recognition. Action recognition aims at recognizing the human action in a video. And so compared to images, videos have an additional temporal dimension. Thus, they have rich modalities. Here we demonstrate 4 modalities in videos, like the RGB frames, optical flow, scatter, and audio. Among these modalities, scatter is a coordinate sequence of human joints. It is a compact representation that is closely related to human activities. The scatter-based action recognition has received increasing attention in these years. And here is a definition of scatter-based action recognition. It means recognizing an action solely based on the human scatter sequence. Broadly speaking, using eye landmarks for gaze estimation or using hand landmarks for gesture estimation, and they are all scatter-based action recognition. For scatter-based action recognition, the advantages and the limitations are both quite clear. First, you should use scatter-based action recognition only if it is possible to recognize the action only based on the scatters. A simple counterexample is differentiating several eating something actions. In that case, you can make correct predictions only if you can recognize something. While the advantages are scatter-based action recognition is very light and can be more robust than RGB-based ones when training examples is scarce or highly biased. Here we demonstrate the computational efficiency. Scatter-based action recognition is much lighter than RGB-based ones in both parameter size and flops. The table shows that the parameter size of a scatter action recognizer is 10 times less than an RGB action recognizer. Instantiated with the same 3D CNN backbone, a scatter action recognizer can process a 6 times longer sequence with much less computation consumed than an RGB action recognizer. The scattering data fed to the action recognizer can be obtained via various approaches with no need of manual labeling. NTU-RGBD dataset uses a Kinect sensor to collect the 3D scatters, while the collected scatters are noisy and of low quality. Another approach is to use 2D pose estimators to extract 2D scatters in a video. There exist lots of open source pose estimators, such as OpenPose, HRNet, and the user can select one according to the efficiency accuracy trade-off. Besides, the estimated 2D poses usually have better qualities. The third solution is motion capture. One can use mocap devices or vision-based mocap to obtain 3D key point coordinates and use them for action recognition. As a long-standing topic, there exist multiple solutions for scatter action recognition. Generally speaking, there are 2 main paradigms, the GCN-based approach and the CNN-based approach. The GCN-based approach uses a spatial temporal graph ConvNet to process the coordinate sequence directly, while the CNN-based approach first converts the joint coordinates to pseudo heat maps, generates a pseudo image with color coding or stack the heat maps to form a heat map voxel, and process the pseudo image or clip with a 2D or 3D CNN. Okay, so let's start from the CNN-based approach. Portion is a representative scatter action recognition approach based on 2D CNN. To convert a scatter sequence to a 2D pseudo image, it adopts color coding to squeeze the temporal dimension. A key point at different time steps will be aggregated into a single track heat map, while different time steps correspond to different colors. The track heat maps are concatenated along the channel dimension to form a single 2D image, and then processed by a lightweight 2D CNN. Though carefully designed, the aggregation conducted by Potion leads to severe information loss and inferior recognition performance. To alleviate the drawback of Potion, we propose a 3D CNN-based framework, PostCon3D. PostCon3D uses 3D heat map volumes to represent the scatter sequence and uses 3D CNN for scatter processing, keeping all the temporal dynamics losslessly. Basically, the framework consists of 3 steps. First, a top-down pose estimator is used for extracting high-quality 2D poses and save them as coordinates, which contain the locations and the confidence scores of each joint. Second, we generate 2D pseudo heat maps based on the saved coordinates and stack them along the temporal dimension to form 3D heat map volumes. And finally, we adopt an arbitrary 3D CNN to process the heat map volumes and get the action predictions. Let's first look at post extraction. Post extraction is a critical step for scatter action recognition, and whose importance is often overlooked. We conduct extensive ablation study on the post extraction step, and you can refer to our paper for more detailed results. There are 2 main observations. We first find that 2D poses usually have superior quality compared to the 3D ones, which is significant in both qualitative and quantitative studies. Thus, we mainly use 2D poses as inputs in this work. Besides, we also find that action recognition doesn't need perfect pose estimation results, as long as action patterns can be revealed. For example, we can find lots of obvious mistakes in fine-gene pose estimation results, but it doesn't affect the accuracy of scatter-based action recognition. We choose to save the extracted 2D poses as coordinates and restore them to pseudo heat maps in later processing. In experiments, we find that storing poses as coordinates instead of heat maps is a good trade-off. Enormous amount of computations can be saved while the degradation in performance is just moderate. Yeah. And to restore coordinates to pseudo heat maps for each joint, we generate a Gaussian map centered at the joint location. Specifically, in the previous step, we save the location xi, yi, and the confidence score ci for each joint. And now we generate a Gaussian centered at xi, yi with the maximum ci. K Gaussian maps from a pseudo heat map form a pseudo heat map with K channels, while T pseudo heat maps are stacked along the temporal dimension to form a 3D heat map volume. We then propose 2 techniques to handle the redundancy. To reduce spatial redundancy, we find the smallest bounding box enclosing all 2D poses, crop frames with the box, and resize them to a target size. By doing so, more information can be reserved within a small spatial size. To reduce the temporal redundancy, we use uniform sampling to replace the commonly used fixed drive sampling. To get an n-frame clip, we divide the video into n equivalent segments and randomly sample 1 frame from each. We find the new strategy is especially beneficial for scatter action recognition. PostCon3D can use an arbitrary 3D CNN to process the heat map volumes, and it's much lighter than 3D CNNs for RGB. We illustrate the PostCon3D instantiated with slow only. In 3D CNN adaptation, we find 2 good practices. First, the input should have a small spatial size and a large temporal length. Second, a thinner and shallower network is sufficient for scatter processing. We further propose RGB PostCon3D for the early fusion of human scatters and RGB frames. It is a 3D CNN with 2 pathways, processing scatter and RGB respectively. With bidirectional lateral connections, RGB post-Conv3D significantly outperforms the late fusion baseline. To demonstrate the effectiveness of post-Conv3D, we conduct extensive experiments on 9 different scatter action recognition benchmarks. We first compare post-Conv3D with a representative GCN approach, MSG3D. Both approaches take 2D scatters extracted by HRNet as inputs. With fewer flops and smaller parameter size, post-Conv3D achieves strong performance on multiple benchmarks. Beyond strong recognition performance, post-Conv3D also has several unique advantages compared to GCNs. First, it is robust to noises in post-estimation. In experiments, we try to randomly drop a key point from each scatter with a certain probability. In such case, the testing performance of post-Conv3D is far better than GCN. Besides, when using pulses from different sources for training and testing respectively, post-Conv3D generalizes well across all the settings we tested. Second, post-Conv3D can scale to multi-person scenarios efficiently. In group activity recognition, since multiple scatters occur in the same heat map volume, no extra computation is needed with increasing persons. Meanwhile, the computation amounts of GCN scale linearly with the number of persons. Third, using 3D CN enables a wide design space for intermodality fusion, benefits action recognition with multiple modalities. And combining the key point stream and the limb stream, post-Conv3D achieves the state-of-the-art performance on multiple benchmarks. We also achieve strong performance on action recognition based on multiple modalities, and you can refer to our paper for these results. And here we summarize the advantages of post-Conv3D. With 3D CN, post-Conv3D is of good spatial temporal modeling capability and has unique advantages in robustness, scalability, and interoperability. Meanwhile, there still exists some worth exploring directions, which includes extending the framework to 3D scatters and better architecture design to improve the efficacy and efficiency. That's all for the introduction of these CN-based approaches. There also exist lots of scatter action recognition algorithms based on GCN. Among them, STGCN is one of the earliest and the most representative GCN-based algorithm. Most designs of STGCN has been adopted in most of the following works. So we first briefly introduce these general designs. GCN-based approaches directly take the coordinates of human scatter sequences as inputs. When there exist multiple persons, it models each person independently and averages the scatter features before the last classification stage. A GCN recognizer is a stack of multiple GCN blocks. Like a ResNet is a stack of multiple basic block or bottlenecks. STGCN stacks 10 GCN blocks for scatter modeling. As the network goes deeper, the channel dimension expands while the temporal dimension shrinks. Each GCN block has a GCN layer and a TCN layer. A GCN layer performs interjoint feature fusion within each single scatter with a coefficient matrix A, while a TCN layer performs temporal modeling with 1D convolutions for each single joint track. Here we show the implementation of the GCN layer and TCN layer in STGCN. You can see that both implementations are quite simple. A TCN layer is just a 1D convolution followed by a BN layer, while the GCN layer consists of a 1x1 convolution for feature transformation and a matrix multiplication for interjoint feature fusion. STGCN is a great baseline for scatter action recognition, but lacks good practices and is not equipped with more advanced model designs. In our recently released code-based PY skeleton, we improve STGCN in both module designs and the training practices and present STGCN++. The old STGCN used a single 1D convolution with kernel 9 for temporal modeling, which consumes relatively large amounts of computations and lacks flexibility. In STGCN++, following recent works like MST3D or CTR-TCN, we adopt a multiple branch TCN with different receptive field sizes for each branch. In the new design, assume there exist n branches. The channel width of each branch is only 1/n of the original TCN. By adopting the multi-branch design, both efficacy and efficiency can be improved. For the GCN layer design, the old design adopts sparse coefficient metrics derived from manual skeleton topology for joint level feature fusion and revise the metrics with learnable edge weights. In STGCN++, we only use the predefined topology for initialization and keeps the coefficient metrics as learnable parameters. We find the recognition performance can be improved without the sparse constraint. Besides, an additional residual link is added. The new GCN layer design improves the spatial modeling capability while requires few additional computations. Here we summarize other good practices adopted by STGCN++. For pre-processing, basically, we follow the recent state-of-the-art CTR-TCN, which includes shifting and rotating to align the center and the spine. It's worth noting that we also adopt uniform sampling for GCN-based skeleton action recognition and find it quite useful. For hyperparameter setting, we adopt the commonly used cosine annealing scheduler and use a relatively large weight K. Here we show the recognition performance of STGCN++ on the standard NTU-RGBD benchmarks. The 4 stream results are reported. We also list the ranking on paper-space code. The improvement is quite significant with all those model designs and good practices adopted. STGCN++ can achieve better or comparable performance compared to the previous state of the art. We reiterate that STGCN++ is just a simple and strong baseline for skeleton action recognition. It is not a complicated so-called sorter model. The key to the success of STGCN++ is quite simple and doesn't rely on any complicated attention schemes, data-dependent coefficient metrics, or other complex modules or training schemes. And if you are interested in PostCon3D or STGCN++, the 2 skeleton action recognizer we presented, you can scan the QR code and find more details in our papers. Besides, all codes for the 2 models are released in our skeleton action recognition code base, PY skeleton. And here is a brief introduction to our newly released code base, PY skeleton. It is a comprehensive toolbox for skeleton-based action recognition. It implements 2 different algorithms and benchmarks them on 9 different data sets. Our implementations are simple, compact, and elegant, with multiple existing or original good practices included. We provide ready-to-go pivotal annotation files for users, and you can directly run training and testing for each algorithm with these pivotal files. Besides, we also provide tools for skeleton visualization and annotation generation for custom video datasets. So after introducing all those powerful skeleton action recognizers, there seems to be a depressing fact. The performance on traditional benchmarks seems to be nearly saturated. Most testing cases are correctly classified, and the remaining failure cases are really hard and almost impossible to be recognized by scattering only. So personally speaking, I think the future research in scattering action recognition should focus on the data efficiency and the computational efficiency instead of focusing on improving recognition accuracies on standard benchmarks. First, we talk about data efficiency. It has already been validated that strong recognition performance can be obtained when there exist hundreds of training samples per class. But what if it comes to dozens or even several samples per class? The new setting can be challenging and worth exploring. A possible solution is self-supervised pre-training on massive scattering data. Those scattering data can be automatically generated with pulse estimation and massive web videos. Note that the success of data-efficient scattering action recognition may directly lead to lots of customized applications. For example, you can register a brand new gesture with only several video clips, and then the perception system can successfully recognize it. The second challenge is computational efficiency, which is closer to engineering. We already demonstrate that scattering action recognition itself is quite computationally efficient. Combining it with a fast detector and a pulse estimator, one can get an efficient perception system for human-centric video analysis, and that can be quite useful. Of course, we know that scattering itself may not be able to handle all action categories, and how to combine scattering with other modalities is also a worth exploring topic. When we combine other modalities with scattering, our goal is to utilize other cues in videos like object or scene, while keeping the good properties of scattering-based action recognition, like the good robustness or the computational efficiency. General multi-stream late fusion may help to improve the recognition accuracy, but most of the good properties do not exist anymore. A simple solution I'm working on is to extend the spatial temporal graph and add diversified features into the graph. For example, we can use object detectors to extract the object features and scene classifiers to extract the scene features and add them as nodes in a larger spatial temporal graph. This framework can be used for various applications such as recognition, retrieval, or self-supervised learning. And that's all for my talk. Thanks for your attention. If you are interested in the introduced topic, you can send me an email or find me at my poster tomorrow. It is at tomorrow afternoon, and my poster is at 40B. And again, thanks for your attention.
Okay, thank you, Haodong. So that's all for. Is there any question about the scattering based action recognition? So feel free to ask if you have any questions. Yeah. So. So if there is no questions, so then that's all for today's CVPR tutorial of the OpenMMLab. So thanks all the speakers for your sharings, and thank you all for the friends online for attending this tutorial. So see you next year. Hopefully we're gonna meet on site in the next year. So that's all for today. Goodbye, everyone.